All right, so try this for today. We've got this little sheet in front of you that says discuss the continuity of each of the following functions, and let's do that. Let's talk about continuity. We just spent the day figuring out what continuous meant, drops and punctures and things like that, and as you look at these functions, which ones of them, and maybe I had to go off screen, which ones make you think continuous? Is this continuous? Why, sure. Y equals x, continuous. It's 3, sure. X cubed, sine, those are all delightfully continuous functions, right? Okay, so let's start there. The top row, those are continuous functions. X plus 3, if I shift this guy up 3, seems reasonable, right? 5x, great. X cubed plus x, what's that going to do? Is that going to be continuous? Maybe it will. Yeah, I think so. Any reason that it wouldn't be? Anything you can look at? 5 times the sine of x. It's just going to be a taller version of this curve, isn't it? I've gone off camera. Oh, terrible. I'm looking like I'm hovering way too close. But anyway, 3x cubed, so I just took this one and multiplied it by 3. These are all sort of reasonable. This one, 3 divided by x. Continuous except when x equals 0. Cube root of x, continuous everywhere. X cubed minus x, sure. Sine of x cubed, sure. Ooh, whenever sine of x is equal to 0, we'd have some issues, right? Okay, so generally speaking, we can look at functions. We can expect to know when they're continuous. Let's go to the other machine. See you later. All right, so properties of continuity. As we move through these, we just did that piece. We're going to talk about what makes a continuous function a continuous function. If f and g are continuous, then these are also continuous. Some multiple of a continuous function. We talked about that with 5x and 5 sine x. If you look back at that other sheet, maybe tear that off the front or something like that, they're also continuous functions. Okay? If we have 2 continuous functions, the product of those continuous functions is also continuous. So continuous function x sine x, or even 5x, product of 5 and x, is a continuous function as well. So multiplication of continuous functions gives us another continuous functions. If I add or subtract them, sum or difference of a continuous function, I get myself another continuous function. Okay? Mouse, I'm not sure why, but let's go with here. If we look at, the ones we talked about, x plus 3, x was a continuous function, 3 is a continuous function, add them together, get another continuous function. Continuous function plus continuous function gives me another continuous function. You see the pattern? Okay. So this is the one where we had a little so we had some, let's try that again. Rewind. All right, so this is the one where we had some issues, some places where we said, oh, it's continuous except when. So we looked at the last one was x cubed plus 3 over the sine of x, and for that particular one, whenever the sine of x went to be 0, this wasn't a continuous. Okay, so quotients are continuous functions. The quotient of continuous functions is continuous as long as my denominator doesn't equal 0. Okay? We looked at, I think, 3 over x is another possibility on that sheet. Doing all right? So which functions are continuous? If I look at a function, can I just say, yeah, continuous, or no, not continuous? Well, yeah, the continuous functions, we get your polynomials. They're always continuous. We've got your rational functions, which are always continuous as long as this is not equal to 0. My rational functions are continuous. My radical functions are continuous when they're defined. So the square root's defined as long as x is positive, so as long as what's underneath is positive, so that's fine. But once they're rolling, radical functions are fine. My trig functions are also continuous as long as they're continuous at least on an interval, because sine's continuous, cosine's continuous. Tangent has some breaks in continuity, but other than those places where, tangent, remember, is grades backwards, sine over cosine. So tangent's not going to be continuous whenever the cosine is equal to 0, right? And that's what's going on here. That's basically goes back to that rational function theory. Okay, so most of the functions that you're familiar with are pretty much continuous functions. So we do something funky with them. Composite functions are continuous. So as long as the inner function is continuous at that particular value that we're talking about, and that the function's continuous at that place. So composite functions, think of the sine of x cubed. X cubed is continuous. Sine of x cubed is going to be continuous. X cubed is continuous. The square root of x cubed is going to be continuous as long as x cubed is a positive number. Okay? So if x cubed goes negative, then we've got some issues. All right? The intermediate value theorem. You've seen this before. You just may not realize it. If my function is continuous on some interval, and this is a closed interval, includes the endpoints a and b, and k is a number between the f of a and the f of b, then there's at least one value, c, such that a is, or c is between a and b, such that the f of c is equal to k. Let's draw some picture. So we've got some continuous function, like so. Okay? And there's point A, and there's point B. Okay? And so we can get out there's the f of A, and there's approximately the f of B. Okay? So k is some number between these two. Okay, k is someplace on this line. So they're saying that somewhere between a and b, there's someplace c, and I don't know where it is, and it doesn't really matter. This is most of our calculus theorems are what are called existence theorem. They don't necessarily tell us how to find an answer. They just tell us that the answer exists. So somewhere in here, there's a value of c that would equal there. That would equal that. So we're going to say it's right there, but it doesn't really matter. I randomly picked a c value. But the basic, it goes back to the blob theory. I can't get from here to there without passing through that middle number. So I can't get from the f of a to the f of b without passing through k. And the way I got to the f of a was through a. Where I get to the f of b was through b. So somewhere c is in the middle. Okay? Can't get there from here. Can't get from 0 to 100 without passing through 50. Sound familiar? Ooh. I'm really surprised. I know you have that on your screen already. So show that there's a 0 in the interval in that function in the interval from 2 to 4. Okay? So here's what we want to know. We want to know that the function's continuous, and it is continuous because it's a polynomial. So that's what we would say. That's the first thing when we're trying to use the intermediate value theorem. Then we check out the f of 2. So I plug 2 into here. The f of 2 is -1. The f of 4 is 3. Okay? Trying to show that there's a 0 somewhere in between 2 and 4. So y equals 0 is in between y equals -1, and y equals 3, right? I can't get from -1 to 3 without passing through 0, can I? Okay, so the function's got to pass through 0 somewhere between those, and there you have it. You can read that, can't you? Okay, my y value is below 1 or below 0 here, above 0 there. On a continuous path, is there any way to get from -1 to 3 without passing through 0? I think not. I think not. Okay, there's the intermediate value theorem. Okay, in this case, instead of going from 0 to 100, we went from -1 to 3. So, intermediate value theorem. Okay, those are the problems for tomorrow. That's what we have, I guess. We talked about continuity. We talked about the properties of continuity. Nothing really too earth-shattering there. So, I think that should just about do it. We'll wrap up for the day. We'll hopefully see you tomorrow. If you have questions, you know that you should ask, and we'll keep moving along. Thanks. Have a good evening. Thanks for living. That's the one I wanted. For such a fabulous closure, but I blew it. Here we go. Talk to you tomorrow.